In this video, I'm looking forward to sharing with you basic statistical concepts that are in the CFA syllabus, including the difference between population and sample, but we won't take it for granted. There are many samples, but only one population. We'll look at the 4 measurement scales, including nominal, ordinal, interval, and ratio, and we'll hover on the essential difference between a ratio and interval scale. Hint, it has to do with the origin. We'll look at frequency distribution and the usual suspects that are measures of central tendency, mean, median, mode, but also other measures of the mean, including weighted, geometric, and harmonic, including we'll look at an actual application of computing the harmonic mean to compute the average price paid for a security, and we'll finish with the specific definition and how we would compute a quantile of a univariate data set. And I'll show you also that it matches the Excel function percentile.exclusive, not Excel's percentile.inclusive. So I'm looking forward to that. What is the nature of statistics? Well, very broadly, we could say there are 2 methods, descriptive and inferential, and they are a 2-step, which is to say in practice we usually do both. We do the descriptive and then we go on to the inferential. Descriptive is when we turn data into information by summarizing a large data set. I tend to think of this as what is modernly and commonly called exploratory data analysis, EDA. If we think about it, when we import or receive a large data set, in raw format, the large data set is very difficult to communicate efficiency. It's very clunky. We don't really use the large data set to communicate to our users, for example. So that's the job of descriptive statistics. It gives us some numbers that are essential features of the large data set, which can be very familiar features like the average, the maximum, the minimum. And those statistics can be quickly, efficiently consumed by our users, telling them the essential contours of the large raw data set without actually having to go into it. However, descriptive statistics doesn't really doing a job for us yet. It's just telling us a story about the data. That's important. But inferential statistics, the way that I think of it is then that's when we go do a job with our data. And it's also called statistical inference, and that's when we make a forecast, estimates, or judgments using probability theory. It is important in statistics to really be comfortable with the distinction between population and sample. I can say over a decade of teaching statistics that it is very important definitional and semantic distinction, because if you're not comfortable, confusion will definitely follow in some of the more intermediate advanced topics. Too often, students glance over this, but it's very important. The population is all members of a specific group, and it's however we've defined the group. We can define many different groups, but to have the population, we need to have all members of the group, and then a descriptive measure of the population characteristic is called a parameter, hence the term population parameter. So I might visually, as I've often done, draw a square rectangle to represent the entire population. In practice, the entire population is unknown to us. It may even be unknowable. Or if it's knowable, it would be expensive and or time-consuming to access it, even in this era of big data. And so for practical reasons, we simply do not have all the members of the group. We simply do not have the population, and so we take a sample or we observe a sample, which I might represent with a circle. The sample is a subset of the population, and here's an important implication of this. If we've defined the population as a certain group, then every time we went back to look at the population, we would get the same rectangle, right? But the sample, if we observe it randomly or drawn it randomly, you can see how we should not expect to get the same sample every time. We would get a different sample. I'll draw one that's overlapping, but here's another one that's not. And so there should be many different possible samples, but only one population. And in practice, we observe a sample and we're trying to make an inference about the population that's unknown or unknowable to us. So sample statistics is a quantity computed from a sample and used to describe it. So if we take something like the average, we might have an average of this sample. That's a sample statistic, but it's going to be different from the average of this sample. So our sample mean, see how that's a sample statistic? We naturally should expect that to be different or to fluctuate each time. There isn't such thing as a single sample mean because there are many different samples. But we might measure the sample mean as a sample statistic in order to make a guess or make an inference about the unknown population mean, which is a population parameter. However, that population mean, we did not expect it to change. Many different sample means as sample statistics used to infer the nature of the one unknown population parameter. As we use numbers to describe things like sample mean or sample standard deviation, it's important to be mindful of the different measurement scales. Here they are ordered from weakest to strongest, starting with nominal. That's where we have categories, but they are not ranked. My example here, hard to see, is hedge fund strategies. So the hedge fund universe can be divided up into different strategies or categories. And so in data science, we would call this categorical data. And we might find there are some hedge funds that have an equity market neutral, and others might have an arbitrage or fixed income convertible arbitrage. Many different categories. However, there is not really a ranking. We wouldn't really say that equity market neutral has a higher ranking, or we wouldn't naturally assign to it a higher number than a credit arbitrage strategy. Categories but unranked would be nominal. And then if we want to go up the chain, I'm going down the page, but I'm going to stronger level of measurements, we would have the ordinal scale, which is categories and they are ranked, as opposed to nominal categories but unranked. Classic example of an ordinal scale are credit ratings. Think Moody's and Standard & Poor's, where we do have categories. A category we would AAA, and we have another category, single A, and we also have double B. Just three of the many categories. These are different categories, and they are ranked. It can be said that AAA is higher credit quality than single A is higher credit quality than double B. And numerically, in fact, the default probability of AAA would be lower than the default probability of single A and double B. So here we have categories, and they do have a ranking, and so we could call that an ordinal scale. Next, we would have interval scale, where we do have numbers that are ranked, and the difference between the scale value really applies as we move up and down the scale. Here, the classic example is, I've got a thermometer because the classic example is temperatures. Both Celsius and Fahrenheit are interval scales. So what I mean is that we have a 0 Celsius, which is the freezing point of water. We have 10 degrees, 20 degrees, and the difference in temperature between 20 and 10 is the same as between 30 and 20. The difference between the scale values is equal. So this is Celsius. We do have interval data. However, it's not ratio scale because, well, a way to look at this is that the 0 here is not actually the absence of temperature, and therefore we can't use ratios on this. What I mean there is 30 degrees Celsius is not 3 times the temperature of 10 degrees Celsius, because these are not ratios, because this 0 is not a true 0 point at the origin. Put another way, it's not actually the absence of temperature. So when the true 0 point is the origin, when the origin or 0 really does signify an absence of the quantity of variable in question, in that case we can use ratios, and we have a ratio scale. Oftentimes we summarize the data with frequency distributions. That's a tabular display of frequency of data into intervals. This is a way to summarize large data sets and ultimately into a histogram. But the steps there are to sort the data in ascending order and then calculate the range. That's not something we select because the range is the difference between the maximum and the minimum value. And then something we do select or decide is the number of bins or intervals. I believe the CFA calls them intervals. I like to call them bins. I think it's safe to say you can call them bins or intervals, but that is something that the user or the designer of this information gets to decide, although a lot of software will decide that on default, although in practice then we end up modifying it because if you take a histogram, the selection of the number of bins oftentimes has a surprisingly profound effect on the display of the histogram. So we pick the number of bins, the range is computed from the data, and that means there is a bin width associated with any number of bins, which is simply the range divided by the number of bins. And notice here a tip, we round up to ensure that the final interval or final bin will include the maximum observation. Then we chain the intervals by successively adding the interval width to the minimum value. We count the number of observations within each bin or interval, and then we construct a table of the intervals from smallest to largest with frequency of observations in each interval. So that's where we're constructing a table. But alternatively, we could leave the bins in order and just show a histogram. So here we go, simple example. We have 12 observations, and we might have collected them in whatever order, but here they've been sorted from lowest to highest. The lowest value is negative 3.87. The highest is 11.78. And you can see there, that's our maximum and minimum. The difference here, 11.78 minus 3.87, is our range. We didn't need to make any decisions on that. Where we would make the decision is K, the number of bins. In this case, we select 4. So there are different ways to go about that. One method would be to take the square root of 12 and round that up. Sort of a handy rule of thumb that I happen to like. Square root of 12 is 3.5, and that rounds up to 4. That would give us 4 in this approach. Oh, excuse me, the interval width. So then we've got the range divided by 4 is 3.9, and or some, that's probably itself rounded. But then remember that tip, we would round that up to get the interval width that we're going to use. So we round the 3.9 whatever up to 4. So based on 4 bins or intervals and this range, we're going to use, we've determined that the width of each bin or interval is 4. And so here's the construction of the intervals starting at negative 3.87. We add 4, that gets us to 0.13. And so then here we chain, we add another 4 to get 4.13. We add another 4, we add another 4, and then we're done because we decided that there's 4 bins. That gets us to 12.13. And because we rounded up here, that 12.3 is going to encompass here our maximum value, 11.78. So then we have intervals. Here we might call them A, B, C, and D. And we just have a count. Our first interval or bin runs from negative 3.87 to 0.13. And we would count how many are in that bin. And you notice it's observations that are less than or equal to this value and less than this value here. So we've got, in terms of that first bin here, 1, 2, 3, and 4. I could have just drawn it. 1, 2, 3, 4. And that's our frequency. Same and so on, 4, 4, 1, and 3, 8. And as a check here, after we do this at the end, 4 plus 4 is 8, plus 1 is 9, plus 3 is 12. That matches our 12 observations. Okay, we look good. There is our frequency distribution table. So then we'll go and apply some terminology here. We've already said that the bin or interval is a set of values within which an observation falls. We have the absolute frequency. That's just the actual number of observations in a given interval. And then notice relative frequency just is the absolute frequency of each interval divided by the total number of observations. And then we have the cumulative, which is really just a running total of the absolute, both in terms of raw numbers, frequency, and in terms of the relative numbers. So we also have a cumulative frequency and a cumulative relative frequency, although it's probably just easier to observe these. Here we have a table frequency distribution of equity returns for, it looks like 19 different countries, and they're the corresponding arithmetic mean for each country. So really we have, just for each of 19 observations, we have a single value. And you can see the intervals or bins have been defined thusly, starting at 5% and going up to 10% with a bin width of 1%. Such that here we have the absolute frequency. So three of these countries, have an arithmetic mean that falls into the bin of 5 to 6%, 4 of them 6 to 7%, and so on. So here the absolute frequency is just the count of the observations, or in this case countries, that fall within that bin. So that's absolute frequency. Then we have relative frequency. And here that just takes for this first bin of 5 to 6%, that's 3 divided by the total of 19, the total count or number of observations. That would be our sample size is 19. 3 divided by 19 is 15.79%. So that we could say among this sample of 19 countries, about 15.8% of them have a mean real equity return that falls within this bin of 5 to 6%. Cumulative absolute frequency is simply the running total. So if we get down, let's say here to the 12, then what we're saying is 12 of these 19 countries have a mean here that is, you could see it's cumulative, so less than 8%. Cumulative less than. And similarly, we have cumulative relative frequency. So we could say of the 19 sampled, 63.2% of them, about 63.2% of the sample has an arithmetic mean that's less than 8%. A histogram would be the most common way then to represent these relative frequencies or absolute frequencies. So that's just the bar chart representing the frequency of the distribution, and it will allow us to visually inspect very efficiently the nature of this data. And as I mentioned, it's an interesting point that selection of K has a surprisingly profound effect on the visualization of the histogram. So in practice, oftentimes we do end up modifying the K in order to get what we think is a more appropriate or realistic depiction of the distribution. We can also use a straight line to plot the midpoint of each interval on the x-axis and the absolute frequency on the y-axis, and then just connect those neighboring points into a straight line. To my knowledge, that's less common. And then the cumulative frequency distribution simply plots that cumulative frequency quantity, so that this needs to be, you can see this is going to be an increasing function because it's cumulative. So measures of central tendency, these tell us where the data are centered. Of course, these are very typical, although there's more than one. Arithmetic mean, median, mode, and we have some other concepts of the mean. The arithmetic mean, of course, very popular. This is the sum of observations divided by the number of observations. And you will notice here that we have, keeping in mind that distinction between a population and a sample mean, that mathematically we have the same. When we go to average, we average a sample in the same way we'd average a population, right? We sum the values and divide by the number. Although I would ask you to take note here of the difference in the variables. Here we have, for the population, what's being used is Greek mu, and that's because Greek, by convention, Greek letters are used to signify population parameters. And over here, very typical, these are both by far commonly used. In fact, for population sample mean, in my opinion, it would be unusual to see different expressions than here. Greek mu for the population mean, and then for the sample mean, you'll notice what we're getting is a Roman X with a bar on it, and that the Roman, by convention, Roman letters are used to convey sample statistics, right? We started off by that distinction. What we have here, although the math is the same, this, just seeing this X bar tells us this is a sample statistic. Just seeing this Greek mu, by convention, connotes, if not denotes, for us that this is a population mean. What might that mean in practice if I hearken back to what I originally said about the many samples that are making inferences about the one population? Well, one thing we would know then is that this sample mean itself would fluctuate or vary based on which sample we go back. We go back for another sample, we'll get a different value. And in this way, we know that this sample mean here is itself a random variable with the fluctuating values that would be used to make to draw an inference about or try to estimate what this population mean is. But this population mean here isn't really a random variable. It's something we don't know, but it's not really changing for the given definition of the population. So for example here, it really does depend on how we define it. If we say let's take all of the Costcos in a city, and in my example, there's only 3 Costcos, and we want the average profit margin. Well, if we get them for all 3 Costcos and take the average, of course, that's not all Costcos in the state of the country, but in terms of how we've defined the population, we've gotten all the members in the population, and we could call this a population mean. After all, if we go back and remeasure it in just 60 seconds, we should get the same answer. As opposed to if these were 3 Costcos out of 10, we draw a random sample. If we went back and did another sample of a different 3 out of 10, of course we're going to get a different sample mean. And so over here, an example might be PE ratios of 6 companies within a certain industry. Let's say the industry has 50 companies. We get the PE ratio, we compute a sample mean, we get 19.33. Mathematically the same. We summed the values and divided by 6. But we know if we went back to the industry of 50, collected a random sample of 6, we'll get different companies, we'll get a different sample mean. But we might do that for several trials. We might in each case be trying to basically illustrate what is the mean for the industry without actually having exactly measured it. Properties of the arithmetic mean include that the sum of the deviations around the mean is 0. Mathematically, that's given this way. After all, if we take the average, if we take the sample mean and multiply by the number of observations, by definition, we're getting the sum of the observations. So here, the sum of the deviations can be expressed here as the sum of the observations minus the sum of n sample mean observations. But if we take the sample mean and add it together n times, well, that itself is n times the sample mean, which is the sum of the observations. And so we've subtracted the sum of observations minus the sum of observations. We need to get a 0. A key drawback of the arithmetic mean is that it's sensitive to extreme values, what we might call outliers. And then we also have the median. So this is the value in the middle. This is the middle observation of sorted data. Key advantage of the median over the mean, and in fact, in practice, oftentimes why we might use the median instead of the mean, is that it's not affected by extreme values are what we call outliers. On the other hand, it doesn't use all the information about size and magnitude of observations, right? So that's interesting. The mean is not distorted by outliers. However, it in a way uses less information. And in this example here, we have on the left 7 observations, or here's the raw, let's say, observations as we observe them. And then in the second column, I didn't label it, but this is just the sort, right? The lowest one is going to the top, and then the next value, and then the 2.32. So same 6 observations sorted. And then over here we have, same 7 observations sorted. And then over here we have 8 observations raw, which have then been sorted. And they're the same observations. And the only difference here is that we have an additional observation. And it looks like it's the 3.79 is the extra or 8th observation here on the right. And so with respect to the median, on the left, when we have an odd number of observations, like when we have 7, the median's real easy. It's the value right in the middle. So it's the 4th observation, and you can see how it's symmetrical because there's 1, 2, 3 above it and 1, 2, 3 below it. And the observed 4.35 is the median. So when we have an odd number of observations, the median is in fact one of the observations. Here on the right, we have an even number of observations. It's 8. And so you could just see here, the average doesn't fall here on the 4th. It follows right between the 4th and the 5th, because that's where we have 4 below and 4 above. The median is the average here, the average of the 3.79 and the 4.35. The median here is 4.07. And then of course, because it's the midpoint between these two, the median is not itself one of the observations if we have an even number of data. And then just to go back and reinforce this point here about pros and cons of the median, let's say I don't really have extreme outliers, but you'll notice that if this, let me just clear this, if the 0.55, let me just change that. Let me just say that was a dramatic -9, -9.9. If this observation 6 here was a -9.9 instead of 0.55, it would still be the first value here instead of this. And the median would be unchanged. The extreme outlier here would not change the median, and in many cases we would say that's an advantage. On the other hand, it hasn't really incorporated any of that information here about size and magnitude of these observations, especially the outliers, which in some cases might be a disadvantage. The mode is simply the most frequent. So if here we have a series of data, the mode is the one that occurs most frequently, which happens to be, well, at first glance, I might think it's a 4, but a 4 occurred only twice, whereas the 3 occurs 1, 2, 3, 4 times. 1, 2, 3, 4. The 3 is the most frequent observation, and so it wins the vote in terms of the mode. Very straightforward. Weighted mean is extremely important. In this example, we have equity and bonds. Maybe our allocation is 70% to equity, 30% to bonds, and they have very different returns. And so the weighted mean there would be the 70% multiplied by its return plus the 30% weight multiplied by its return, negative 0.5%, equals, in this case, negative 20.52%, such that the nature of the weighted mean is let's assume these returns are fixed. As we shift the allocation and vary the weights, our weighted mean will be different. The weighted average of forward-looking data is something that we could call the expected value. The geometric mean is the nth root of the product of n observations, and then the geometric mean return. Notice the difference here. This has a return. Here is the product of 1 plus the returns. So we're chaining together 1 plus the returns. and taking the 1 over to the raised to the 1 over t power, subtracting 1 to get the geometric mean return. And so in this example, a very classic, we have annual numbers. And so this is, in that case, when the periods here are annual, this application of the geometric return is what's called a compound annual growth rate. So that, right, we're getting here 1 plus negative 24.33%. We're multiplying that by 1 plus 29.67%, right? So obviously that's, if I just come back here, that's 0.757. We're multiplying it by 1.2967, multiplying that by 1.1543, and so on. So we have the product here of 5 values, and then we're raising that to the 1/5 power and subtracting 1 to get a geometric mean return, which in this case is, we could also call, because these are annual periods, we also call this the compound annual growth rate, or CAGR. And a way to think about that is if we started here with $100 and then it were to compound at 1 plus the CAGR of 2.85% over the 1, 2, 3, 4, 5 years, then we would get, I got $115.08. And that is the same amount we would get if we just manually took the $100 and lost 24%, and then on that base gained 29%. So if we manually went through the gain, loss, gain, gain, loss, gain, we would end up with $115.08. And that's the same amount as if we just compounded the CAGR here, which is a geometric mean return. The harmonic mean is a special type of weighted mean in which the observation's weight is inversely proportional to its magnitude. So I think it's hard to follow the English description of how to compute the harmonic mean. So on the next slide, we have a simple example. But the steps are, we just sum the reciprocals of the observations, we divide the sum by the number of observations, and then take a reciprocal of that average. Right, so if x is the value, its reciprocal is 1 over x. So summing the reciprocals is a summation of the 1 over x is, I'm not worried about the subscript. We divide that by the number of observations, and then take the reciprocal of that is equivalent to, you can see, just n over the sum of the reciprocals. And in fact, that's the way it looks. So the harmonic mean, this to me is much easier to follow than the language that we just saw. The harmonic mean formula is number of observations n divided by the sum of the reciprocals. Actually pretty straightforward. Then here's just an example. An investor purchases $2,000 of a security each month for n equals 2 months. So that means if you're the investor, you invest $2,000 this month, and next month you invest $2,000 as well, the same amount. However, you're buying a stock where the share price was only $15 on the first month when you spent $2,000, so you could purchase 133 shares. On the second month, when you invest another $2,000, the price is doubled to $30, and so you can only get, looks like, about almost 67 shares. So price changes, you invest the same amount. What's the average price paid to the security? Well, the average price paid to the security when you spent $2,000 at $15 per share, and then when you spent $2,000 at $30 per share, your average price paid is the harmonic mean of $20 per share, because that's the harmonic mean. 2 divided by the sum of the reciprocals, 1/15 plus 1 divided by 30, and that should equal $20. And now you've spent $4,000 in total, $2,000 the first month, $2,000 the second month. So you spent $4,000 divided by your average price or harmonic mean of $20 per share means you purchased 200 shares. And that's because you got, looks like 133 shares the first time, 133 and a third, and then you added 66 and 2/3 share. So you have a 200 shares. You spent $4,000 in total. Your average cost is in fact the $20. So that's harmonic mean. And then finally, other measures of location, very important, are the quantiles. Quantiles include, depends on where we demarcate, but quartiles, quintiles, deciles, and percentiles. This is the value at or below which a stated fraction of the data lies. The median divides our distribution into half, so the median is the same thing as the 50th percentile. The quartile divides the distribution into 1/4, so that's 25, 50, 75. Quantiles divide the distribution into 1/5. Deciles divide the distribution into 1/10, and percentiles divide the distribution into 1/100. And so quantiles are used in investment research to rank portfolios, performance of investment managers, companies, and mutual funds. So to calculate the percentile, we sort them in ascending order, and where the answer will be given by the yth percentiles, whatever percentile we want, right? If that's a median, then y would equal a 50. If it's the 25th percentile, or let's see what we called that. If it's a quartile, if it's the first quartile, then y would be a 25. We divide that by 100 to get the decimal format, and then we multiply that by n equals 1. If this is a whole number, the location is the actual observation. If it's not a whole number and lies between two observations, then in this approach, we would use a linear interpolation between the observations. And just to make that concrete, we consider this series of numbers here and arranging them in ascending order. So here's the first and here's the last. And if we want the 75th percentile, the answer here is the 12th observation, because in this case, we've taken our 75th percentile is 75 divided by 100, or 0.75, and we multiply it by n plus 1, which is, it looks like n is 15, so we multiply by 15 plus 1, or 16. So this is 0.75 times 16, which equals 12. And our 12 is a round number. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We go straight to the observation. It's a 48. For the 90th percentile, right, where it's 90 divided by 100 multiplied by 16, and it looks like we get 14.4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, I could have known that since this was 15. Here's our 14th, and here's our 15th. It's not a round number, so we're interpolating. So we're going, the distance here between 62 and 76 is, looks like 14. So we're going 40% of that distance, or 40% of 14 is getting added to the 62, and that's 67.6 is our interpolation. I also put this from the spreadsheet in vertical format, if that's easier to follow. And just to show that if you're looking at it from Excel, because I was interested, this definition of the quantiles comports with Excel's percentile.exe, stands for exclusive. It's different than the inclusive, which has a different math applied to it, so it does get a different result. But you can see when I applied the percentile.exe, or exclusive, I get the same result here. That 75%, 90%. In this case, that 0.9 is the 90th percentile is just 0.9 multiplied by my n plus 1, right? It's going to equal 0.9 times 16 equals 14.4. And so then I'm interpolating between these two values, the penultimate value and the lowest value of all. So that's a look at the quantiles, and that concludes this video. And if you found the video helpful, please do subscribe to the channel, and that'll ensure that you get notified of the next video that we publish in this series on the CFA, and you'll also get notified of the other videos that I'll publish. Thank you.